session.
Okay.
Okay. Cool. So hi everyone. We will be recording this session and posting it onto the 140 YouTube channel. Also, these slides will be posted on vCourses files. They're live on vCourses right now. As a final exam review team, we do not know exactly what is on the test. However, the exam will be cumulative and may have material from all lectures, section presentations, and homework. And a note from Gail, she told us she's planning to revise the final exam to ensure it is straightforward. She will prioritize material that was in lecture and homework, and the reading is available to clarify your understanding of the material from lecture, and if you need a different way to explain the same material if needed. However, Gail has confirmed that she won't be asking questions that are in the reading and not covered in lectures or sections. And a reminder that the final exam is on Monday, May 11th, and the Zoom link will be posted on vCourses and provided later. All the final exam updates is on the vCourses page. So we're going to dive in with the first main concept, which is energy use and green buildings. It's important to know the order of magnitude for these numbers for energy and carbon. Buildings account for 72% of U.S. electricity, approximately 40% of energy use, 40% of total CO2 emissions, 40% landfill material, and 13% potable water. So also not doing Berkeley times because we have so much freaking material to get through. Looking at this pie chart, again, it's important to know that buildings account for 40% of all U.S. energy use. Space heating and cooling plus lighting is on the order of 1/2 of building energy use. You do not need to know these detailed numbers. So we've shown this inverted triangle quite a lot. It's important that we set priorities for low energy buildings. Reduce heating, cooling, and electric load. First, and then passive systems second. Efficient active systems next, and then renewable energy is always done after everything else. Renewable energies are often considered as an important aspect, but it's important that we reduce loads first. Okay, so I am now going to pass it on to Eric to talk about thermal comfort.
Okay, hello.
Eric, are you going to lose me? Cool.
I am. Can you not hear me?
No, got it.
You can hear me. Okay. So, are you seeing the regular view or are you seeing my presenter notes as well, just to confirm?
Regular view.
Okay, good. So, thermal comfort. What is thermal comfort? The ASHRAE definition, that condition of mind which expresses satisfaction with the thermal environment. But in fact, it is typically measured as a result of indexes that try to look for discomfort as opposed to comfort. So in an engineer's view, comfort means that you don't have any degree of discomfort. And this obviously is a bias that changes the way that it's measured. Thermal neutrality or thermal delight. So Lisa Hirschong's thermal delight in architecture gives us a new way of thinking about what richness we might be able to add to our environment, which is not simply neutrality. So if you are just looking to avoid any impressions of your thermal environment, then you don't get thermal delight. Major variables influencing thermal comfort are environmental or personal. On the environmental side, you have the air temperature, humidity, air velocity, and the mean radiant temperature, which we'll talk about in a minute. On the personal side, you have metabolic activity, how much energy your body is using and turning into heat and clothing, insulation around your body, both of which have units, met and the clo. Air temperature is generally a form of heat exchange that is dominated by convection with your body, and convection ensures mixing of the air so that, generally speaking, you get air that is of a relatively similar temperature in locations that have lots of convection. Radiant temperature is the surface temperature of the surfaces that your body can, quote unquote, see. So this is the view factor. The mean radiant temperature, so as we know, you're constantly exchanging back and forth with all objects around you, radiation, long wave radiation that is in fact heat leaving your body, heat leaving a wall.
Here, let's use
Are we getting a comment right now?
the cleaner I got today. Just 'cause it's bleach.
Can somebody mute themselves? Are we good? So you're constantly exchanging heat by radiating heat out yourself and getting heat radiated back at you. If a surface is cold, it doesn't radiate back at you nearly as much as a warm surface. The mean radiant temperature is the concept that you can take an average of all of the surfaces to the extent that they see your body. So a surface that's very far away, you're actually seeing a very small percentage of. And a surface that's nearby has a much larger impact. So the simplified equation for operative temperature, which takes into account both the dry bulb temperature and the mean radiant temperature, is that you add these two together and divide them by 2. So you just take the average of the dry bulb temperature and the mean radiant temperature, and that is a sort of a simplified understanding of what a person would feel in a particular environment. So it's not just the dry bulb or air temperature, but it's also all of the radiant surfaces around them that they're exchanging with. How is subjective comfort measured? So ASHRAE thermal comfort standard 55. The goal was to create a comfort zone in which 80% of people describe themselves as comfortable. And so if you go on this 7-point thermal sensation scale, that means you want 80% of people to feel slightly cool, neutral, or slightly warm, as opposed to hot, warm, cool, or cold. This is highly subjective because, in fact, some people would describe comfort outside of these 3 categories. Some people prefer being warm, but this is how the comfort is objectified. Conventional versus adaptive model of thermal comfort. So it was ASHRAE RP, and you don't need to know any of these specific numbers, RP 884, that started collecting data. And there are, this was the standardization of data that was then applied across the entire database. But the conventional method that is this ASHRAE, are you feeling discomfort or not in a closed room, is being replaced at this point by a more nuanced adaptive comfort model, in which the access that people have to the environment. Somebody is speaking. Can you mute somebody, Jackie? Thanks. So adaptive comfort is when a person has access to the outdoor environment by being able to, for example, open their window and engage with outside conditions. They're willing to tolerate a wider range of interior temperatures. So in fact, allowing people to engage with their environment means that they sometimes don't need to have the AC up as high or the heat up as high. Psychrometric chart review. So the psychrometric chart is this friend of ours from Climate Consultant, with which we are all intimately familiar, having seen it many times. It quantifies on 3 different axes, or 2 different axes and an interrelation, the humidity of air and the temperature of air. So you've got these vertical lines, these vertical red lines, each of which indicates a dry bulb temperature, which is to say what you would think of typically as temperature, that thing that you see in your weather report. On the other axis, what you might think of as the y-axis, you have a humidity ratio. Sometimes this is expressed as a ratio, sometimes this is expressed as an absolute value of humidity. And then the lines that are moving across, oh, okay, Astro Benny, please mute. The lines that are moving across on a diagonal are indicating enthalpy lines at which there is, or no, those aren't enthalpy lines. Sorry, those are relative humidity lines, which humidity ratio, temperature, relative humidity lines. The curved line, of course, on the top is when the air is totally saturated, and if you attempt to either add humidity or cool the air, you will, at that point, have condensation. And then the enthalpy lines are lines on which the energy in the system is the same as the temperature changes, but the humidity changes correspondingly to preserve the same amount of energy. So if you are cooling without any sort of condensation, then what happens? Well, you can see that from point A, where we're at 40% relative humidity, we cool, which is to say we go left on the x-axis, down from 80 degrees to 60 degrees. Suddenly, if we're at 60 degrees and we have the same total amount of humidity, this is 80% relative humidity, whereas it was only 40% in the first temperature. Why is this? Because hot air can hold more moisture. So as we cool the air, the relative fullness of moisture of that same air increases. Cooling with condensation happens when you cool air so far that you get to this 100% relative humidity curved line, at which point droplets will form and condense liquid water out of the vapor state that is in the air if the temperature gets any further towards the cold direction. So if you then cool down beyond point D, you must lose relative humidity. You must lose absolute humidity because you are at the maximum relative humidity. And that absolute humidity loss is precipitated out in the form of liquid water. The building bioclimatic chart is a concept that can be very useful for seeing the most efficient passive cooling and heating strategies based on whatever particular climate a building is in. So this chart explains the range of what we might perceive of as thermal comfort, this darkly outlined area. This is the typical thermal comfort zone. The building bioclimatic chart shows propositions for how in a particular climate you can increase that range into other areas by using certain strategies. And you'll notice that a lot of these strategies have similar names to those that you saw in Climate Consultant and worked with for your design project, because it's the same idea that you have in the Climate Consultant chart for passive strategies. Okay, so shall I transition to Sierra?
Great, sounds good. Would you like to stop sharing your screen? Cool. Can you see my screen okay?
Yes, indeed.
Great. So, I'm going to start talking about thermal mass. Thermal mass has to do with the capacity materials have to store thermal energy for extended periods. So thermal mass mainly stores energy, and that lets you moderate indoor temperature fluctuations, reduces heat flow through the envelope, and also reduces and shifts peak loads. So this graph kind of illustrates how thermal mass can help with modulating indoor temperatures. So the dark teal curve here is showing the outdoor temperature. The dashed yellow curve is showing interior or internal temperatures with very little or low thermal mass. And then the slight teal curve is showing with thermal mass the interior temperatures. So you can see there's already a small time lag just between outside and inside, but once you incorporate thermal mass, that time lag increases, so you might even have the peak temperature at night rather than during the day, and then the low temperature during the day, so you're kind of shifting potentially the full 12 hours. And this curve, when thermal mass is incorporated, is also damped quite a bit, so the peaks and the valleys are less extreme as opposed to the outdoor temperature peaks and valleys. And here's some graphics to illustrate that as well. So starting off with a potential typical exam question, which of the following is not a desirable factor when designing for thermal mass? So I'll give you a few seconds to think about it. A, the outdoor temperature swings, having outdoor temperature swings on both sides of the comfort zone. B, mass on the interior, insulation on the exterior. C, mass being well distributed. D, the need for a fast reaction time. And E, nighttime ventilation. So just a few seconds to think about which you might go with. And then the answer is D, the need for a fast reaction time. So because of that time lag, when you incorporate thermal mass, you don't, it's not as useful when you have situations where you want to be able to quickly heat up or cool down space. So that's something that is not a desirable factor when designing for thermal mass. Another typical exam question. So true or false question, thermal mass is most effective for summer cooling in hot, dry climates. Just give a few seconds to think about it. And so the answer is true. Thermal mass is most effective for summer cooling in hot, dry climates because hot, dry climates have those large general temperature swings. So in the summer, you can take advantage of the cool nighttime temperatures in using thermal mass to be able to keep things cool even during the day when things heat up. So there are a few different types of passive heating systems. They're broken down into indirect versus direct. So the direct system has that sun coming directly into the building and heating the interior of the building. There's also a roof pond system where you have a layer of water on the roof, and that can heat the interior through the water acting as thermal mass and then storing heat, which can then radiate to the interior of the building. There's a thermal wall system, which uses the wall as thermal mass, and then that can be heated up through its exposure to the sun, and then using the heat stored in that wall to radiate to the interior. And then also a sun space, kind of a greenhouse area that's glazed to be able to store a lot of heat, and then that can be used to heat the interior of the building as well. So now going into the equations associated with thermal mass. So thermal mass is the amount of energy required to raise a mass 1 degree of temperature. So either use 1 degree Fahrenheit or 1 degree Celsius. And so this equation should look familiar. We used it quite a bit at closer to the beginning of the semester. This equation is saying that energy transferred equals the thermal mass multiplied by the temperature change. So that energy transferred could be in BTUs or kilojoules. Thermal mass is in BTU per degree Fahrenheit or kilojoules per degree Celsius, and then the temperature change in either degrees Fahrenheit or degrees Celsius. It's really important to keep track of your units. You don't want to mix and match like degrees Celsius with Fahrenheit, or kind of losing track of which units you're using. So it's good to always carry those along through your lines of calculations and double check that all your units cancel out correctly, because that's one of the most common mistakes to make in these kinds of calculations, and especially with the final exam being online the way it is, and you're just kind of putting in the final answers. Really important to check units, and that can be one of the best ways to catch your mistakes. So this delta T here, the temperature change that we're looking at, is the change over time. So it's new versus old. And if you take a look at the equation, T new minus T old, if the thermal mass is getting hotter, then T new is higher than T old, and that's going to be positive, and Q gain will be positive. So if that Q is greater than 0, it's a gain. If Q is less than 0, it's a loss. It's good to keep that in mind to make sure that you have your signs correct. So in order to calculate thermal mass, we need to know a few material properties about the material we're looking at. So you can either use specific heat capacity or volumetric heat capacity to find thermal mass. And which one you choose depends on whether you know the density or the volume of the material. If you know the mass, you want to use a specific heat capacity because that's in BTU per pound degree Fahrenheit or kilojoule per kilogram degree Celsius. So it's per a certain amount of mass. So then you can combine that with how much mass you have to find the thermal mass. Whereas if you know the volume, you would use the volumetric heat capacity, which is per cubic feet or per cubic meter. So that's per the amount of volume of the material. And also if you know the, you can kind of work between these using the density as well to work between volume and mass. So if you are given the volume and the volume and the specific heat capacity, but not the volumetric heat capacity, you can still work between those using density. And so to find that thermal mass, you would use either specific heat capacity times mass, specific heat capacity times density times volume, or volumetric heat capacity times volume. So you can always make sure that you're using the mass and volume versions correctly with the right kind of pairs. So then bringing that thermal mass together for calculating the energy stored, so then we can plug in for thermal mass either specific heat capacity times mass times the change in temperature, or volumetric heat capacity times volume times the change in temperature, or specific heat capacity times density times volume times the change in temperature, just depending on what a particular problem gives you as known values for how much of the material there is. We can look at the material properties of a few different materials and how their specific heat capacities and volumetric heat capacities vary, and then think about how that would affect their performance as a thermal mass material. So water has a volumetric heat capacity of 62, whereas air has one of 0.018. So that's water's specific heat capacity is 3,000. Water's volumetric heat capacity is 3,444 times greater than air's. So you definitely want to keep in mind at least that order of magnitude, and knowing that water is able to store a lot more heat than air is for a particular amount of the material. So you've probably seen this image several times now. And this is just showing that relationship between air and water, and how if you wanted to be able to store the same amount of heat, you would need only this tiny little glass of water to be able to store that heat. But if you're using air, you would need these 2 big bags of air. So you need a much greater volume to be able to store that much heat. So now we're going to go into an example problem, and I'm going to go over a few example problems in the review session today, and I'm going to go through them kind of quickly and focusing just more on the process. But if there are questions and you'd like me to go into more detail, I I can return to them at the end too. But you've also seen,
Sierra,
yeah.
sorry. So there was a question about the typical exam question. I'm wondering if we should ask, or we should go back to that now or after the thermal mass section.
Sure. One of the like multiple choice or true or false questions.
The first one on slide 28, the what is not a desirable factor when designing for thermal mass. Right, so she was asking why the other factors were desirable, especially B and C.
So for B, having thermal mass on the inside and then insulation on the exterior is kind of able to keep that heat that's being stored from escaping. So you're kind of insulating it a little bit. And for C, having the mass well distributed, like there could be different ways to approach it, but having the thermal mass well distributed would be kind of like having lots of small heat sources throughout your building rather than just one that has to spread more widely. So that could make it more effective in terms of heating or cooling the interior of the building. Does that answer the question?
She said thank you.
Cool. Sorry, it's hard for me to see the chat while I'm presenting, but yeah, feel free to ask questions and I can stop and go back to, yeah. So going back to our hot tub problem. So we've done some similar ones early in the semester. So this is going back to that hot tub in the courtyard of Worcester and looking at two main things: how much it will cost to heat up the hot tub, and then how long it will take for it to be ready for the happy hour when the plan is to use the hot tub. So we're given some information. We know that we want to raise the water temperature from 58 degrees Fahrenheit to 102 degrees Fahrenheit. We know that we're using a 4.6 kilowatt heater to supply the energy. We know that our hot tub has a volume of 324 feet. It's 9 feet by 9 feet by 4 feet. So when we're thinking about how much it'll cost, we need to know how much heat needs to go into this hot tub to be able to heat it up where we want to the temperature that we want it to be at. And we also that involves knowing how much thermal mass is kind of contained in the water. And so for thermal mass, we're going back to that equation for either a specific heat capacity times mass, or a specific heat capacity times density times volume, or volumetric heat capacity times volume. And you could kind of just remember one of these and know that if you had to switch between mass and volume, you'd go to volumetric heat capacity. Using specific heat capacity and density, you can incorporate volume. So they're kind of all the same, but just using either mass or volume and making sure that you are using the right equation for your particular known values. So for this problem, we know the volume. And so we're given this table, and this table does not have volumetric heat capacity, but we do get specific heat capacity and density. So we can find water and find the specific heat of water and the density of water. And then we can use those to plug into that equation. So we plug in 1 BTU per pound degree Fahrenheit for specific heat capacity, 62 for density, 62 pounds per cubic foot, 324 cubic feet for volume. And that gives us 20,088 BTU per degree Fahrenheit. So that's our thermal mass. So now we know the thermal mass. That can allow us to calculate how much heat is going to be stored, needs to be stored to be able to heat up this thermal mass, the requisite number of degrees. So going back to this Q equals thermal mass times delta T. So thermal mass, 20,088 BTU per degree Fahrenheit times that 44 degree Fahrenheit increase equals 883,872, with those degrees Fahrenheit canceling out. So it's in BTU. So that gives us how much heat or energy we need to put into our hot tub to be able to heat it up as much as we need it to. But then now we want to calculate how much it will cost. So for the cost, we happen to know that kilowatt hour of energy costs $20 or 20 cents, not $20. And so first we convert our known energy to kilowatt hours. So 1 kilowatt hour equals 3,414 BTU. So going from 883,872 to 258.9 kilowatt hours. And with 20 cents each, that costs $51.78. So, and just to focus in on energy versus power. So it's really important to remember whether you're working with power or energy in these problems, as distinguished by the Q dot or just the Q without the dot. So Q without the dot is energy. It's kind of more energy stored in either BTU or watt hours or joules, whereas power is the rate of energy that's being transferred. So then we have the Q dot, and it's for energy per a certain amount of time. And so that would be in BTUs per hour or watts, or some other unit of power. You could also rearrange the equation so energy equals power times time, kind of depending on what you're solving for. And we also might sometimes write Q dot as Q per hour, because sometimes it's hard to write in that dot. So then trying to figure out how long will it take to heat up our hot tub. So we know that energy, the 258.9 kilowatt hours, and we know the power that we're transferring energy in at, the rate of energy transfer to heat up this hot tub. That's 4.6 kilowatts from our heater. So we know from the previous slide that power equals energy over time. So rearranging that, time equals energy over power, time equals the 258.9 kilowatt hours divided by 4.6 kilowatts. And that gives us that it will take 56.2 hours to heat up our hot tub, which seems way too long. And I think we need to look for a different system. Cool, so now I will pass it off to Jackie to talk about heat transfer.
Okay. So now we're going to talk about heat transfer mechanics. What happens to material when heat is added or removed? It's either sensible heat, which is temperature change, or latent heat, which is phase change. Energy is transferred through a change in state. So that goes from solid to liquid to vapor. And this shows the progression of a higher energy state. Sorry, just organizing my windows here. Okay. Water is a typical unit of measurement to study sensible versus latent heat. For 1 pound of water, you can look at sensible heat. It takes 1 BTU to raise 1 degree Fahrenheit. For latent heat, it takes 141 BTUs to melt ice to water and 970 BTUs to evaporate water to vapor. So that's how you can see the massive amount of energy when you do phase changing. Gail noted that she will not be having any calculation questions about this. However, you do need to understand the concept. So these are the 3 different types of heat transfer mechanisms, and they are simply ways by which thermal energy can be transferred between objects. And they rely on the basic principles that kinetic energy or heat wants to be at equilibrium or equal energy states. So I will unpack these in the next few slides. So first we have conduction, which is heat transferred through contact. This is typically solid materials. You can think about touching a hot pan. Then there is convection, heat transfer through fluid, most commonly probably through air. So the hot air above a fireplace is through convection. And then lastly, we have radiation, which is heat transfer through electromagnetic radiation, all of which we will go into more detail. Again, conduction is heat transferred through contact, and heat flow equals conductivity divided by thickness times area times delta T. And delta T is the difference between hot and cold temperatures, because air always wants to be in equilibrium. So when you're looking at object properties versus material properties, object properties is dependent on the amount of material. And you can see object properties have a similarity in how they are used. So there is mass, which is an object property, but another trend is that words ending in ant. So resistance, or you don't say it like that, resistance, conductance, so the A-N-D-E. And then you have material property, which is independent of amount. So things like specific heat capacity, density, resistivity, conductivity. Not know there's animation, but there you go. Okay, so examples of material is K, which is conductivity, and an example of material needing an object amount is R. So when you're looking at the water and air properties, conductivity versus an object like 1/4 inch glass or 8-inch concrete block, or the most common value that we probably know, R value. An example that you always need to check your units, and that this is an inversion of units. The ability to conduct versus the ability to conduct versus resisting heat flow. So you need to know how to convert between these material properties. Equations will be given on the useful info sheet, but you need to know what these mean. As a rule of thumb, conductance is the inverse of resistance, so that is quite helpful. So convection is the second type, which is heat transferred through a liquid, which can be explained with air films on surfaces. So the heat flow is air film conductance, or you can call it the coefficient, times area times delta T. Again, conductance is the inverse of resistance. So the R value of air film is the inverse of conductance H. When you are including an air film, you have to look in the problem whether it says summer or winter, indoors or outdoors. This is quite important because the numbers are very different. Okay, so the last one is heat transfer through electromagnetic radiation. This is the electromagnetic radiation spectrum, where shorter wavelengths means increasing energy. The only band of radiation we can see as humans is visible light. So there are two types of radiation, solar radiation, which is short wave, and radiant energy from the sun, solar sun. This includes UV, visible light, and near infrared. Secondly, there's terrestrial radiation, which is long wave, terrestrial Earth. Earth radiated from every surface on, or energy radiated from every surface on the Earth. And as it is with heat transfer, there's always a net transfer from warm to cool. And then this is a comparison between solar radiation, and you can see the higher energy state with the sun being 10,000 degrees Fahrenheit and 0.5 micrometers versus terrestrial radiation, Earth, which is 80 degrees Fahrenheit, 10 micrometers. This red highlight zone is all heat but no light. So wavelengths that are longer than solar infrared or near infrared is heat. So there are two ways that radiation interacts with a surface. First, radiation strikes a surface. So this is called incident radiation. Incident radiation will hit a surface and will be reflected and then the Greek letter is rho, absorbed, alpha, or transmitted, tau. So the formula, adding all these together, reflection plus absorption plus transmission equals 100%. And the 100% represents the original incident radiation. Opaque surfaces do not transmit radiation, so the value for T would be 0. Therefore, when you're looking at this equation, it's just reflection plus absorption equals 1, or 100%. Very important to note, glass is opaque to long wave radiation. So we will talk about that more in the following slides. In addition to radiation hitting a surface, radiation also leaves the surface. So this is in comparison to the incident radiation concepts we were talking about. Total energy is emitted from an object. Total energy emitted from an object is underneath that curve on the chart. The maximum amount of energy emitted is called the perfect emitter, or black body. We do not use this formula in this class, but this is kind of like a conceptual framework for something that perfectly emits radiation. Okay, so since perfect emitters is a conceptual framework, real materials are not perfect emitters. They have an emissivity coefficient, which is a long wave property. So emissivity is the efficiency with which a material emits long wave radiation. It is independent of color, and the emissivity of most materials is approximately 0.9. And that is for everything except for metals, which are 0.05 to 0.2. So Kirchhoff's law states that emissivity equals absorptivity for the same wavelength. So emissivity equals absorptivity for long wave radiation. So we'll relate this to low E windows. So going back, glass is opaque to long wave radiation. So we take the incident formula for opaque surfaces where transmission equals 0. So that means the Greek letters translated, absorption plus reflection equals 1. And then when you flip that around, reflection equals 1 minus absorption. Then you take Kirchhoff's law from the previous slide, where emissivity equals absorptivity, and then the equation becomes reflection equals 1 minus emissivity for long wave radiation. So when you look at the properties for metal, low E films are made with metal-like properties. So low E equals low emissivity, and that means emits less long wave radiation. And then when you're looking at the formula, low E equals high reflectivity, which means that low E films reflects more long wave radiation. So when you're looking at what glass does for a glass pane, it has high reflectivity for long wave radiation. So this is an example of a low E property in real life. You can also think of her as a burrito or a thermos. But after a marathon, people use emergency space blankets with metallic low E properties. So this minimizes the long wave emitted radiation. And this is a photo of Gail's dog, Toby. After a cold day at the ski slopes, Gail puts these metallic foil sunshades to reflect, to maximize the reflection of Toby's long wave radiation back to him. Everyone loves this chart. It's a comparison between emissivity, reflectivity, and absorptivity. So looking at the different corners, let's start with the perfect dissipator. So it absorbs 0 solar and emits max long waves. So that means that these materials typically have very cool properties from heat loss. Now we're going to look at black body, which absorbs all solar and emits max solar. And then lastly, we're going to look at the perfect collector, which absorbs all solar and emits 0 long wave radiation. So this is a direct contrast to the perfect dissipator. It has very warm properties from the heat gain of absorbing all the solar. And here you can see some examples of how, real life examples of where things are close to these perfect dissipators, perfect collectors. Okay, so starting with perfect dissipator, and a common example is white cool roof coating. So that creates a cooler atmosphere, basically, for the Earth, for urban heat island effect. Then we have the black body, and you have the perfect emitter, and that is independent of color, and an example is clear glass. So that's an example of why clear glass is terrible, because it absorbs all the solar heat and emits maximum. So it's bad in both hot and cold climates. And then we have the perfect collectors, which includes spectrally selective black coating for metal solar collectors. So so you can collect as much solar energy as possible without emitting all the energy out into the atmosphere. And then you go into white body, which is something that absorbs 0 solar and emits 0. So this includes metals like low E film. So then when you add clear glass with the low E, it gets somewhere in the middle of those two properties because the glass collects solar. Are there any questions that people want to ask about this before we move on?
Which part is urban heat island effect? Like
the one that combats urban heat island effect is the white cool roof coating.
Okay, I see.
Yeah, because it doesn't absorb the solar radiation, but emits maximum. So that means that you're not putting all the heat into cities with a lighter roof coating.
Makes sense, thanks.
Yeah. Okay, cool. I'm going to pass it on to Sierra, who will talk about heat transfer in a wall assembly.
Cool. Okay. So now looking at the kind of building application of a wall assembly, if we look at a kind of example wall assembly with brick and then maybe some insulation of some sort and interior surfacing. If it's warm on the inside and cold on the outside, this is what the temperature profile might look like through the wall. So on the inside, it's at 70 degrees Fahrenheit, kind of a comfortable indoor temperature. But then as the heat, as you kind of move through the different materials in the wall builds up, the temperature goes down and it kind of drops linearly with these different slopes along the different, through the different materials. And the slopes of those, that kind of temperature drop depends on the resistivity of the different materials. So you probably remember from earlier in the semester, we talked a lot about series versus parallel heat flows. So when heat flow is in series, the heat is passing through one material at a time, kind of sequentially. So first it passes through material 1 and then through material 2. Whereas with the parallel heat flow, it's passing through multiple materials simultaneously. So in a building, you might see these as, with series, you might have a wall with insulation and brick, kind of that previous example. And so heat is passing through first the maybe insulation and then the brick in series, one after the other. Whereas another part of the wall might have studs in it. And so in that part of the wall, it's heat is passing through a different path. So then you have those two different paths in parallel. So it's good to always make sure you're checking whether the heat flow is either in series, in parallel, or both. So this is what it might look like if you have both kind of going on. So for these three main parallel heat paths, we have A, B, and C all in parallel, but each one is broken down into a series of materials where the heat is passing through them in series. So for C, first it's passing through this one and then several more. So when you're calculating the, when you're looking at U values and R values, you would want to first look at the materials in series here. And so for materials in series, you add the R values. So each of these 5 materials would have a different R value, and you would add R1 plus R2 plus R3 plus R4 plus R5 to get the kind of total effective R value for path C. But then if you want the whole, this whole block here of U values, you would need to then take into account the fact that you have these 3 paths in parallel. So you found the total R value for C. To get to U value is 1 over R value. So inverting that R value to get kind of U value for C. And then going through the same process for B and A. So you have 3, you have kind of U value for A, U value for B, U value for C, and then you can add those U values. So you add R values in series, but you add U values in parallel because U values are the inverse of R values. And so on this topic, we can kind of go back to thermal bridges, which kind of throughout the semester. And so when we're thinking about conductivity or insulating values in buildings and wall assemblies, thermal bridges are a big concern for buildings. So thermal bridge would be when you have a material that's a good conductor, like a metal running from the inside to the outside of the building, or connecting a good portion of the through the kind of wall assembly. So you're able to, so that thermal bridge kind of becomes a highway for heat transfer, and heat can pass through it really quickly, and you end up losing a lot of heat through that particular path, even if you have insulation kind of in parallel with this thermal bridge. So these images here show a building that struggled with this issue because of these floor plates which stick out, and they have metal on them, which make them turn them into thermal bridges that kind of conduct heat right out of the building. So no matter how hard they're trying to heat or cool the inside of this building, all of that energy is just kind of being released out to the exterior through these thermal bridges. And this could have been easily solved without having to sacrifice the design of the building by having a thermal break between the kind of inside floor plate and where it reaches the outside. So you'd want to always make sure that you don't have these conducting materials reaching all the way from the inside to the outside. And that requires a really detailed look at all of the detailing and connection points in the building. So when we're thinking about what insulation to choose for buildings, there are a lot of different factors to consider. There's the price, whether insulation is fire resistant, if it's likely to encourage mold growth, how durable it is, if it's water resistant, the sustainability of the material, if it has a lot of embodied carbon or not, and whether it could be recycled potentially. So there are a lot of different factors to take into account a lot of different installations to choose from as well. This is a list of some common ones. So there's a lot of considerations to take into account when choosing what kind of installation to use for a building. And they all have different pros and cons and depend on the building's particular priorities. So we're going to do a quick example applying that series heat transfer. So we're looking at this particular wall assembly here, which has gypsum board. It has 3.5-inch fiberglass insulation, and then it has 3/4-inch plywood. And we're looking at what is the R value for this wall section in the winter, and then what is the U value. So it's really important to take into account these air films. So there's an outside air film and an inside air film. And that's where you'll see a difference in the winter versus in the summer. So, and we always want to make sure that once you've calculated the U value that we've taken into account those air films. So the U value should always have taken into account those air films. So in order to calculate the R value, so we know that these materials are in series. The heat will pass through, as heat is being transferred through the wall assembly, it'll pass through to them sequentially. So we know we need to find the R values and then sum those up for the total R value. So looking into the table from the appendices on B courses, which I believe is similar to the one that you used in your homework, you can look up the R value for the inside air film in the winter, the 1/2-inch gypsum board, 3.5-inch insulation, 3/4-inch plywood, and then the outside air film in the winter. And kind of here, this is where the sources came from. So to find the total R value, we sum those up and we get 13.23 hours square feet degree Fahrenheit per BTU. And then to find the U value, we invert the R value. So U value equals 1/R total, and 1/13.23 is 0.08 BTU per hour square foot degree Fahrenheit. So this is just kind of going over that series heat transfer. So when we have all these materials in series, we sum up the R values, RI plus RA plus RB, all the way through the number of materials we have in series to get our total. And those units are always going to be hours square feet degree Fahrenheit per BTU. And then the U value is the inverse of R total, so 1/R total, and the inverse of the units. But don't invert them first and then add. The order is very important to sum the R values first and then invert, rather than inverting each individual R value and adding. Not only is that more difficult, it's not the order we want to do it, so you always want to sum the R values first and then invert to find the U value, because those will not get the same answer, kind of reversing the order of operations. So now looking at this whole building envelope loss, what are the 3 main ways that we lose heat through a building envelope? Those three main ways are through conduction, both in series and in parallel through the wall assembly. We lose heat through the perimeter, through the kind of slab edge. And we also lose heat through infiltration, air moving in and out of the building in uncontrolled ways. So starting off with conduction heat loss. So drawing on those principles of heat transfer in parallel and in series, we're working towards this sum of the UA values to characterize our wall assembly's ability to insulate or conduct heat. So in order to get there, we want to first identify the different paths we're looking at. So in this example, there's one path through the wall assembly where it's kind of exterior. And Jackie, now's the time to switch or do a new recording according to my timer. So sure. So path 1 is through this insulation without any studs, and path 2 is through the studs without any insulation. We want to treat those as 2 separate paths, and first look at one of them, say the insulation path, and find the U value from the R values in series. So we'd find the R value for the air films on either side, these two materials, and then the insulation, sum those up, and then invert it to get the U value for path 1. For path 2, we do the same, just with the studs instead of the insulation. So summing up those 5 R values and then inverting for the path 2 U value. So then we have those 2 U values for the different paths. They each have different areas associated with them depending on how much area is kind of allotted to just insulation versus the framing of the building. So we would take the path 1 U value multiplied by path 1 area, and then also take the path 2 U value multiplied by the path 2 area, and then sum those together. And that sum is this sum of the UA. So we're summing the U of the insulation multiplied by the area of the insulation with the U of the wood or framing multiplied by the area of the wood or the framing. So now that second mode of heat transfer through the slab. So this is a really complicated mode of heat transfer with these kind of radial paths of heat transfer. So in order to calculate this easily, we simplified it down using this F perimeter edge loss factor. So this can be looked up in tables and it kind of encapsulates this complicated heat transfer process so that we can use it easily in our calculations. So some common values for an uninsulated slab would be 0.81, for insulated 0.55. And then along with knowing that perimeter edge loss factor, you can just multiply that by the perimeter to get the heat loss through the slab. So it's really important to use the perimeter and not the area. So for this equation, we're interested in perimeter and kind of the length of that slab edge around the building. So Q dot slab, or the heat loss associated with the slab, is the perimeter edge loss factor multiplied by the perimeter length. And the final mode of heat transfer is through infiltration. So there are a few different ways a few different things that might lead to infiltration in buildings. So you might have wind-driven flow, and this depends on a lot of things like wind speed, wind direction, shape of the building, if there are different cracks in different places, what the surrounding neighborhood looks like, if there are a lot of tall trees and buildings or hills, or if it's flat and open and the wind can really pick up speed. So that depends on a lot of different things. You might also have stack-driven flow leading to infiltration. And so that happens because hot air rises, and so then cold air kind of comes in, leaks in from the bottom. So that also leads to these pressure differences that can bring a lot of air infiltration in and out of the building. So when we're looking at heat loss through infiltration, we can use this kind of handy measure of infiltration, which is air changes per hour, or ACH. And so that the units of air changes per hour are 1/hours. And that's because air changes per hour are the number of times the air within a particular space is replaced in 1 hour, replaced with outdoor air. So those units are kind of per hour. So in order to calculate the infiltration heat loss, we're using kind of a variation of the thermal mass equations we looked at earlier. So we know the volumetric heat capacity of air, and we know the volume of a particular room. And so then with the number of air changes per hour, we're kind of calculating how much thermal mass is in the air that's being exchanged in and out of the building. And so then how much energy is being lost through that exchange of that particular amount of air, that particular volume of air. So that's how we're getting to this equation for heat loss through infiltration. So it's the volumetric heat capacity of air specifically, multiplied by the volume of the room, multiplied by the air changes per hour of that particular building, and then multiplied by that change in temperature. So just as some, to give a sense of what normal air changes per hour values might be, if we had a really leaky house, it could be 2 to 6 air changes per hour. So all of the air in the building might be fully replaced 2 to 6 times an hour, which would be quite a lot. If it's super tight, it could be down to 0.05. So really tight buildings, a passive house might have like 0.6 air changes per hour, and that requires a fair amount of coordination to make sure that everything is being kept really airtight as much as possible. So now bringing all these principles and equations together, we can start looking at the whole building envelope heat loss. So we have these three portions of our envelope heat loss. We have the heat loss from conduction as measured by the sum of the UA values. We have the heat loss due to the slab coming from that F factor, the perimeter edge loss factor multiplied by the perimeter length. Then we have the heat loss due to infiltration. So drawing on the volumetric heat capacity of air, the volume of the space, and the air changes per hour. And these are all multiplied by the change in temperature. So we can pull that out. The parentheses are a little off here, but pulling out that change in temperature, we are summing up these three sources of heat loss, the sum of the UA plus the sum of the UA plus the perimeter edge loss factor times perimeter plus volumetric heat capacity of air times volume of space times air changes per hour, summing those up and then multiplying all of that by the change in temperature. And so all of those factors are, those represent characteristics of the building only, independent of the climate, whereas this change in temperature, because it is including the outdoor temperature, is dependent on the particular climate the building is in. And so together, the sum of the heat loss from conduction, the perimeter from infiltration, is our UA ref, hopefully a familiar phrase or term by now, and that's in BTU per hour degree Fahrenheit. So now returning to our hopefully familiar example of the one-room house problem. So this is where we kind of apply this equation of Q envelope loss equals UA ref multiplied by the change in temperature. And we're applying this to a simple one-room house, and using this equation and kind of a few other helpful equations to find, first starting with the UA ref, then finding the balance point temperature, then the furnace size you would need for this particular one-room house, the number of degree days in this climate, and then looking at weekly energy use and weekly energy cost. So those are the main goals of this problem. And on an exam, a problem like this, which is kind of follows a lot of different steps, it would be broken up with each different part being kind of a different part of the problem, and also the different parts would not be linked. So if you got UA ref wrong at the very beginning, that wouldn't mean that you would get all of the following parts wrong. So we're unlinking those so that they're all kind of independent ones. But for this example, they build on each other. So we're given a lot of information about this one-room house, from the kind of geometry of the building to air changes per hour, that perimeter edge loss factor, that F equals 0.55, how much of the building walls and ceilings are framed, internal gains, so from the people inside the building or electrical equipment or things like that contributing to internal gains. The design temperature for what kind of like the cold, we're looking at this in a heating context, so a really cold day they would want to plan for and make sure that your systems can hold up to. The thermostat setting, what you want your interior temperature to be at, how much gas costs is kind of the energy source in this particular location. We know the volumetric heat capacity of air. We're given the furnace efficiency at 90%, some weekly temperatures, and then some R values for different parts of the building, for different materials in the building. And these are given as R totals, so it's kind of already summed the values in series, and then we're working from that spot. So we start off by gathering our information about the building geometry, so the perimeter, the volume, the area, and breaking down the area into those different heat transfer paths. So we have the ceiling broken down into the stud portion and the insulation portion. And then we have the walls broken down into stud versus insulation, also windows and doors in the walls. So we can start to fill this in, and I'll go through this pretty quickly because it's a long problem. So we found the perimeter, the volume, and then those different area values using that percentage of area. So we know that 15% of the walls and ceilings are framed. So if we know the total area, we can find the 15% of that. And then the other 85% for the insulation. Then doing a similar process for the walls. So we know the area of the 4 windows and the 2 doors, tracking that out, and then finding the percentage of, knowing the percentage of the wall area that is going to framing, calculating that, and then the leftover area for insulation. So now that we know all those important values for area, volume, perimeter, we can start working on our sum of UA values for the convective heat loss through the walls and ceiling of our one-room house. So for this, we want to sum up all those individual UA values for those different heat paths. So we have the framing of the ceiling, the insulation of the ceiling, the framing of the walls, the insulation of the walls, and then windows and doors. So for each of those, we're either given an R value or a U value. So we're calculating the sum of the UA values. So we want U values for this. So 1 over R for our U values. I think we're given U value for the windows, so that we can just plug right in for the U value. And that sums up to 84.9 BTU per hour degree Fahrenheit. So then moving on to the perimeter edge loss, we know that our F factor is 0.55 BTU per hour foot degree Fahrenheit multiplied by 54 feet. And so multiplying the perimeter, that perimeter of 54 feet by the F factor, we get 29.7 BTU per hour degree Fahrenheit, the same units as this sum of UAs up here. And then for the heat loss through infiltration, we multiply the volumetric heat capacity times the volume times air changes per hour. And so we get 35.6 BTU per hour degree Fahrenheit. And that was with 1.1 air change per hour. So then to get our UA ref, we sum up all of those 3 sources of heat loss. So the sum of the UAs plus the perimeter edge loss plus infiltration heat losses. And together we get UA ref is 150.2 BTU per hour degree Fahrenheit. And with that, we've kind of got this really useful value, which we can use throughout the rest of the problem in this case, or an exam, you would probably be given this for later parts of the problem. But this gets us a long ways towards being able to determine a lot about the performance of the building. So then it brings us to balance point temperature. So balance point temperature, going back to that balance point temperature lab we did earlier in the semester, in the context of a building, it's the outdoor temperature at which heat losses from the building exactly match the internal gains. So it's the temperature when you're concerned about heating, the temperature below which supplementary heating is required to achieve a given set point. And it's important to remember that it's the outdoor temperature that we're looking at for the balance point temperature. So how do we calculate balance point temperature? So the way we do it is by setting so we had that equation Q envelope losses equals UA ref multiplied by the change in temperature. So when we're looking for balance point temperature, we can plug that in as the outdoor temperature and the change in temperature. And so that when we have T balance point is the outdoor temperature, T thermostat or the indoor thermostat setting is the indoor temperature, and we set our losses equal to the internal gain. So we're balancing out how much heat is being lost with how much heat is being gained inside the building. And then we can use that setting internal gains equal to the losses to solve for our balance point temperature. So we solve for balance point temperature, and it's equal to the thermostat temperature minus internal heat gains over UA ref. And working through those units, it's always good to double check and make sure those all cancel out correctly. It's also a good idea, especially with this online version of the final exam, to write out all these kind of calculation type problems on scratch paper and kind of double check before you kind of input your answer for the final time, kind of run through it again and double check your work just to make sure that you catch any potential mistakes along the way. So with balance point temperature, if you have a high balance point temperature, then you are going to have a skin load dominated building. Whereas if you have a low balance point temperature, you'll have an internal load dominated building. And then the question is, do we want a high or a low balance point temperature? So if we're interested in heating, we want to be able to have as low an outdoor temperature as possible before we have to start turning on our heating system. So in that case, which is kind of the main case we're looking at in this class, we would really want a lower balance point temperature. So going back to our one-room house problem and taking what we now know about balance point temperatures, we want to calculate that. And so we're setting the internal heat gains equal to our losses. So setting that equal to UA ref multiplied by the difference between the balance point temperature and the thermostat temperature. And then solving for that, plugging in the values to get our balance point temperature at 56.7 degrees Fahrenheit. So next step, determining the furnace size. So for that, we want to find the kind of peak heating requirements for our one-room house. So like trying to calculate how much heat would be needed on the coldest day to make sure that our furnace is prepared for those extreme conditions. So we're using that 20 degrees Fahrenheit as the kind of design temperature for calculating our peak heating requirements. And so plugging in with our UA ref, our handy UA ref at 150.2 BTU per hour per degree Fahrenheit, multiplying that by the difference between the indoor temperature that we want and that really cold 20 degrees Fahrenheit outside, we can calculate our Q peak as being 7.5 kilobtu per hour. And that should be a Q dot because it's per hour. So then that brings us to degree days. So degree days are an indicator of the severity of winter and summer. So you could either have heating degree days or cooling degree days. We're mostly going to be focused on heating degree days. And so for a heating degree day, it's the units are degrees Fahrenheit days. And you account for them by looking at when the average outdoor temperature for one day is 1 degree lower than the building's balance point temperature. So using that balance point temperature and the kind of average temperature for a particular day and finding the number of degrees of difference over the course of a certain number of days. And you could do this over the course of one day or a week or a month or a year, kind of depending on what time span you're looking at. So we're looking at a week. We were given weekly the kind of average temperatures for a week. So we want to calculate the number of degree days over the course of that week. So for each day, we're looking at what's the difference between our balance point temperature and this outdoor average temperature. And whenever the difference is negative and the outdoor temperature is above our balance point temperature, we don't have to account for that. It's not like we're saving energy when it's too hot to turn on our furnace. We just don't have to use our furnace then. So we don't get any kind of negative degree days for that, having those warmer days. We're just looking at what are our heating degree days, when is the temperature below our balance point temperature. So looking at all of these days, we have the differences for each day, and then we would want to cancel out those days when our outdoor temperature is higher than our balance point temperature. So that would be Thursday, Friday, and Saturday. And then summing the remaining differences, we get that we have 28 heating degree days over the course of this week. So then to calculate energy use over a particular period of time, in this case a week, we can use our UA ref and our degree days to calculate the energy use over that period. So that can be, that's kind of the reason that we were looking into those degree days, and we can use that to calculate our energy use. So, so in this case, we're looking at over the course of a week, we multiply our UA ref by the number of degree days over that week. And then because degree days are in days and UA ref and the energy use are in hours, we want to convert from hours to days. So we know there are 24 hours in a day. So multiplying that 150.2 BTU per hour degree Fahrenheit, our familiar UA ref, multiplying that by the number of degree days, and then 24 hours in a day. And that gives us 100.9 kilobtu, and that's the energy used over the course of this week for heating this one-room house. So then that brings us to efficiency. So efficiency is defined as what you get over what you pay. So usually you're not getting as much back as what you had to put into a particular process. If you tried to power a fan with a wind turbine, you would not be getting strong wind out of the fan as you put into the wind turbine. You're always losing a little bit along the way. And so that's expressed through efficiency. And efficiency is different from coefficient of performance. You can have coefficients of performance over 1 or over 100%, but here we're looking at efficiency. So we're looking at what is the ratio of what you get out in terms of the energy output versus what you had to put in terms of the energy input. So we'll often think about this in terms of appliances and how much energy you have to pay for versus the kind of output that you're getting from it. So looking at our example here, we know that the efficiency of our furnace is 90%. So the efficiency, 90% equals Q out over Q in. Rearranging that, we get Q in equals Q out over the efficiency. So Q in equals 100.9 kilobtus over 90% or 0.9. So then multiplying that out, we get 112.1 kilobtu. So you have to put in 112 kilobtu to get 101 kilobtu out. So to put in a little bit more than we get out. So then to calculate the cost, we know that the cost of gas, and we're using gas for this for energy in this example, is $1.50 per therm. So so then we have to convert from kilobtus to therms, and 1 therm is 100 kilobtus. So converting from our 112.1 kilobtus to therms, and then multiplying by $1.50 per therm, we get that the total cost over this week is $1.68. And then just a final point on this, and the kind of role of efficiency in this process of getting energy from the source to where we're using it. So all the way along the way, energy is being converted from the original fossil fuel that we're burning for its energy. It's being converted into heat, and then steam, mechanical energy, electrical, and then finally being transmitted somewhere, and then being turned into our useful electrical energy. So all in the way, through each of those steps, there are losses, and potentially what you have at the beginning, you might only have about 30% of that by the end. So you lose a pretty significant portion along the way. And it's important to keep in mind that the different efficiencies and costs, these different steps along the way, are a big part of kind of the pros and cons of different energy sources and how much they might cost in different places, depending on the different breakdowns of energy sources a particular area might have. So now I will pass it to Eric, I believe, to work on or go through solar geometry.
Okay. Solar geometry time. So, solar geometry, one of my favorite topics, near and dear to my heart, with which we've all worked quite a bit over these last few weeks. This is going to be a whirlwind, condensed, abbreviated, and short presentation of the salient concepts from this class. So as we know, the sun travels on an elliptical orbit, and the declination of the planet relative to the sun changes throughout the year. This is because the Earth is rotating on an axis that is not coplanar with the orbit axis. This declination And the day length change slowly during the solstices and quickly during the equinox. So as you can see, the declination of the Earth gets moving and comes up to a far faster slope as you're moving towards the equinox. Here's the spring equinox and the autumn equinox. But then in the winter and in the summer, in fact, the declination is changing relatively slowly, which means that also the length of the days is changing less rapidly at those times. The Earth is curved, but the sun is very far away. What this means is that by the time they reach us, the rays from the sun are, for our purposes, considered parallel. Of course, they aren't exactly, strictly speaking, parallel because they aren't traveling from an infinite distance, but they're traveling from a far enough distance that by the time they reach us, wherever they strike the surface of the Earth, they're going to be going more or less on a parallel trajectory. This is why, just as an aside, for those of you who use the pocket heliodons, you can't use a lamp to simulate the sun because the light will spread and radiate out from the point that is emitting the light bulb, whereas the sun is incredibly far away, so by the time it reaches us, all of those rays are relatively parallel. What this means is that if you're standing with the sun directly overhead, which is to say the approach of the sun ray is striking the surface of the Earth at a 90-degree angle relative to a line parallel, rather tangent to the surface of the Earth here, you're going to be getting sun right on the top of your head. If you're at a 45-degree, it's going to be coming not as strongly as on the 90-degree because, in fact, it spreads over a larger area for a given number of rays. So let's think about this in another way. Let's imagine that you have a radiative beam that is radiating 1,000 watts per meter coming from the sun. So you've got, for every meter slice that you would take, you would find that there is 1,000 watts per square meter coming through that area. And if it falls straight on a surface and it's coming on a trajectory that is normal to that surface, which is to say this is a 90-degree angle here, then you're going to be getting that full 1,000 watts over 1 square meter of surface. So 1 square meter is going to get that full 1,000 watts. If it's coming on a 45-degree angle, you'll notice that this, if you take a 1 square meter piece here, if you were to imagine the edges of that 1 square meter projected down onto this plane that it's falling on, in fact, it's going to occupy a larger area, because if this is 1 square meter here, then the area down here is actually going to be the hypotenuse of a triangle, the side of which is 1 square meter. So it's going to be a larger area, and you divide that 1,000 watts over a larger area, which means that suddenly per square meter, you only got 707 watts. Of course, if the sun is shining at a 90-degree angle to the zenith, which is to say it's coming straight from the side, not anything is going to fall on that ground plane, and then you've got 0 watts per square meter. So that should make intuitive sense. Now let's talk about some of these solar angles. There are a whole bunch of angles we've thrown around. The two most important and preliminary angles that we started off with are solar altitude, which is the measurement taken from the horizon going up towards the Earth-Sun line that connects the point that you're taking the measurement from directly to the sun. That's the solar altitude. And the solar azimuth, which is taken, if you were to draw a line straight due south from whatever point you are trying to measure the azimuth for, then you draw a line straight south, and you draw another line also in plan, which is to say on the surface of the Earth, And it is the projected line of this Earth-Sun ray. If you were to just drop it straight down to the ground, then you measure that solar azimuth from south, always starting from south, to that projected Earth-Sun ray in the plan view. It's important to note that when you're saying an azimuth or writing an azimuth in the exam, you always have to say east or west of south. Let's imagine this is a 30-degree west of south azimuth that's indicated here on this graphic. If you just say 30 degrees on your exam answer, it is unclear if you are talking about this angle or this other one here, which is also 30 degrees measured from south, but going in a different direction. So be sure to specify the direction from south of an azimuth angle. Again, these are the two primary angles that you should have as your bread and butter angles: solar altitude and solar azimuth, all measured for a given point of interest that you're saying this is the solar altitude from this point, this is the solar azimuth from this point, and you use this Earth-Sun line in order to generate those two angles. Now let's talk about sun path diagrams. Here is an example of a sun path diagram with all the pieces labeled. You've got, on the one hand, the zenith, because this whole black circle here is a projected sky dome. The center point at the crosshairs is the zenith, which is directly above your head if you are standing at the point of interest for which you are drawing this sun path diagram. That point of interest, you can think of it intuitively as if you were taking a photograph, you're taking a photograph from a place, right? You can't just, you have to choose a specific spot to put your camera. Well, you're putting the camera right here for this sun path diagram and pointing it directly up, and you've got just the right fisheye. You could produce, in fact, a view that would show the sky having a horizon here and the zenith directly overhead. And if you were to leave your camera there and do a stop motion, you could see the sun as it traveled from east to west every day along a line, and it would always fall within this sun path area. Each of the curved lines represents a month or a specific day of the year, a date. The one directly in the middle, which begins on east and ends on west, that's going to be the equinoxes, spring and fall equinoxes. Then the one on the northern side here of east, that's going to be your line for the what we call summer months, which is to say this uppermost line is in fact June 21st, or the summer solstice. The furthest down line is going to be December 21st. Again, you are familiar with this from your sun angle calculators. The azimuth measured from south is moving around this projected sky dome from that line directly due south, either towards the west or towards the east. And on your LOFSACs, those sun angle calculators, you have an altitude overlay, which simply divides into regular increments this full distance, such that if you were to go to this end of that line, you are at an altitude of 0, which is to say the angle measured from the horizon up towards that point that you're pointing at in the sky is 0. You're pointing at the horizon. And as that altitude increases, you gradually point higher and higher up until you are pointing directly overhead. Sun path diagrams are latitude specific. This is something that we have gone over a few times, so I don't think this will come as a surprise. At a 24 north degree latitude, you're going to have some particular image of how the sun moves through the sky over the entire year, right? You've got rising in the east on the equinox, and then setting in the west on the equinox at 24 degrees north latitude. And we can see that it rises at 6 in the morning, it sets at 6 in the evening. If you were to go to June 21st, well, it looks like the sun is rising. First of all, it's rising about 90, 100, 110, 115 degrees east of south, azimuth. And the hour at which this happens, at which the sun could be described as having an azimuth of 115 degrees east of south and an altitude of 0, because it's right at the horizon, maybe 0.001. And it looks like it's just after 5 a.m. By contrast, if you go to a 52 degrees north latitude, in the summer, you're going to be getting the sun rising at 4 a.m., even further to the north, which is to say 130 degrees east of south, which you could also, you could call that, well, please call it east of south. But you could start saying that's actually 50 degrees east of north, because it's northeast. Just as a quick overview of different conditions, if the line has more hours on it on one of the two sides, that is what you would think of as the summer season. So if the line has more hours on the south side of your projected sun path, then you're in fact in the southern hemisphere. If it has more lines on the north side, then you're in the northern hemisphere. If you are close to the equator, it's going to look symmetrical, because if you're on the equator every day, you've got a day that is as long as the night. Example of an equatorial sun path. Each day, the sun rises at 6 o'clock every morning, and solar noon always has the sun in the line pointing south in the northern hemisphere. In the southern hemisphere, it's in a line pointing north, which is to say the azimuth of the sun is, in this case, 0 on those days between September 22nd and December 21st, and December 21st and March 20th. So during this whole season, at solar noon, 12 o'clock, the sun is somewhere in the direct southerly portion of the sky. And then in the other half of the year, it's somewhere in the direct northerly portion of the sky. St. Petersburg, Russia, has by contrast, very, very short day in the winter and an extremely long day in the summer. And in fact, once you get above into the polar regions, then you have a full circle in which during one of the solstices there is no sunrise, and during the other solstice and some portion of time around it, there is constant sun. Where is the sun at noon? Well, at solar noon, the altitude is equal to 90 degrees minus the latitude plus the declination. So we know that the declination, as we saw in summer, on the summer solstice, is plus 23.5 degrees. This is just true for anywhere on Earth. In winter, it's minus 23.5 degrees. So that means that the difference between the maximum and the minimum altitude at solar noon is always going to be 47 degrees, independent of location. What about the full sun path? Well, the On the equinoxes, the declination is 0. So that equation that we just saw, where the altitude is equal to 90 degrees minus the latitude becomes, or 90 degrees minus the latitude plus the declination, suddenly simply becomes 90 minus latitude plus 0. So at the equinox, if you know your latitude, you can very rapidly know what the solar altitude will be at solar noon, when the sun is facing directly due south, or if you're in the southern hemisphere, directly due north. For the azimuth, on the equinox, the sun rises exactly in the east and sets exactly in the west, everywhere on Earth. For the solstices, it's not nearly as regular. This is one of the only parts of solar geometry that you shouldn't be able to wrap your head around as precise mathematics, because it's actually a little bit more complicated. Although it is precise mathematics, it's just not simple precise mathematics. But for the solstices, if you're at the equator, where the days are all equal in number of hours to the nights the entire year, then the angle on either side is the angle between the sunrise on the summer solstice and the sunrise on the winter solstice is going to be 47 degrees, 23.5 south of east for the winter solstice and 23.5 north of east for the summer solstice. At the poles, it's going to be 90 degrees. And everywhere else on the Earth, which is probably where you're going to find yourself, is going to be somewhere in between those two numbers. So at our latitude, for example, the spread is, I don't even know. We're going to find out, because we're going to see that in a minute.
Hey, Eric.
Yes.
We have a question from the chat. Someone asked, why isn't the sun exactly south at noon every day? And this was a question from the Clicker poll.
Okay, so the sun, let's go to one of these sun path diagrams here. So at noon, at solar noon, the sun is directly south in the northern latitude, in the northern latitudes every day. But that's solar noon, that's not clock time. There's a difference between clock time and solar time, which I don't think we have in this review. But the reason for that difference is that we have, when you're looking at clock time, you're actually looking at time zones. So we say, okay, it's the same clock time in San Francisco right now as it is in Reno, Nevada. But we know that the sun sets in the west, and San Francisco is further west than Reno, Nevada. Therefore, San Francisco has sunlight when it's already dark in Reno, Nevada, right? So even if we say it's the same time, you have to acknowledge that relative to the sun doesn't respect these 1 hour boundaries that we've broken the world up into. The sun is just continuous movement. So the reason that at any given place on Earth, if you want to know where the sun is, you first have to determine, well, what's the solar time there? The reason is that it's going to kind of deviate off of this line somewhere, because maybe you're further east on the in your time zone, which means that in fact the sun is not behaving the same. Was that an answer to the question?
Yeah, I think so. And I think that analemmas can kind of show that path as well. Oh,
also that, yeah.
Yeah.
Yeah, I didn't even talk about the analemmas. From what I understand, I wouldn't worry about that level of precision. I don't think that we covered the analemmas in sufficient depth that you should be stressing out about that. But that's just because there's a little wiggle also to the sun as you move throughout as you move throughout the day.
She said thank you.
You're welcome. So, example, sun's path in Berkeley, where the latitude is 38 degrees. Altitude at solar noon is going to always, everywhere on Earth, be equal to this formula, 90 minus latitude plus declination. So, let's say we want to find out on the equinox, when the declination is 0, we want to find out what is the altitude at solar noon. Well, it's going to be 90 minus 38 plus 0. What do we end up with? 52. The summer solstice. The declination is 23.5. 90 minus 38 plus 23.5 is 75.5 degrees. So that is how high up from the horizon you measure an angle in order to point at the sun, which is to say on the equinox, you're pointing a little bit closer to the horizon. On the summer solstice, you're pointing relatively high up in the air. And at the winter solstice, if you do the same calculation, you'd be pointing lower towards the horizon, only 28 degrees up measured from the horizon and pointing south. So sunrise, sunset, azimuth is something that you would get from the sun path diagram. We're not going to calculate it here because, as I mentioned, that's a slightly more complicated calculation to do. So generally speaking, you will just be pulling that off of the sun path diagram. It's always going to be 90 degrees on the equinox anywhere in the world. It's these other two numbers. Where does the sun rise and set on the summer solstice and the winter solstice that changes subtly from 47 degrees at the equator to 90 degrees at the poles. And so you have to actually look that up. Example question. While traveling on the vernal equinox, I noticed that the altitude angle is 41 degrees at solar noon. Where am I? I'll give you a minute to consider this problem. So, if the angle is 41 degrees at solar noon, and it's the equinox, so we know the declination is 0, then we expect the altitude, which is 41 degrees, to be equal to 90 degrees minus the latitude, which is to say the latitude must be 49. 41 equals 90 minus x. You solve for x. X equals 90 minus 41. X equals 49, latitude of Paris, France, or anywhere else along that same latitude. It could be, I don't know, what is the same latitude as Paris, France? Vancouver, probably. So if you were to draw that latitude line around the Earth, anywhere on that latitude line, this statement would be true. Horizon shading masks. Here is the Worcester courtyard. This is a shading mask that has been made of the Worcester courtyard, showing the shading mask in red superimposed on the sun path here in blue. And again, I want to emphasize a shading mask is always made from a point of reference. You typically did this over the past semester from the center point of a window. If you were making a shading mask looking out from a window. But here it's the center point of the Worcester courtyard. And the projected sky dome, here's an illustration that graphically represents that, is just a flattening down of this pretend planetarium, if you will, such that you can have a two-dimensional representation of the sun's path and the objects that are providing shade. All sorts of obstructions are being mapped here. Maybe this is, I think this is what this would be, a tree. Now, angles that relate to a surface orientation. We talked about altitude and azimuth at the beginning. Those are your best friend angles, bread and butter, should know them. There are some angles also that relate to this surface orientation. First of all, this is a term that we've used a lot, that I've used in this presentation. A line that is normal to a surface means that it is at a 90-degree angle to the plane that that surface makes up. And so that line that is normal has an orientation relative only to that surface. South, north, east, and west are not relevant to that description of its surface normalcy. The surface azimuth describes the azimuth measured from south to the line normal to the surface. So in this case, the surface azimuth would be phi, is that a phi? East of south, looks like maybe 25 degrees east of south. The solar surface azimuth is a compound angle because you'll remember this solar azimuth, which is one of our bread and butter angles, and then we've got this surface azimuth, which is just kind of an extra that we're going to add in there. And the solar surface azimuth is the two of these things added together. Why is this useful? Well, because it translates how much of the light from the sun is going to be incident on this surface. So it's going to help us understand what fraction of the radiation is striking that surface. Again, solar surface azimuth is made up of the surface azimuth and the solar azimuth. The angle of incidence. This is the angle at which light is falling on a particular surface. It's measured from the normal to the vertical surface to the Earth-Sun line. So it's cutting through a plane that is neither vertical nor tangent to the Earth. So it's a plane that is unique to that particular surface and a location of the sun. Angles that relate to a surface orientation, one that we have seen covered regularly in talking about shading geometry is the profile angle. You find your location of the sun, which is going to have some azimuth, and you say, okay, well, let's project that sun into a plane that is normal to the surface. So here's that line that is normal to the surface, and we've just projected the sun into that plane. The profile angle is taken from the line normal to the surface, projected to the ground, up to the projected Earth-Sun line in that section that we've taken. Some quick test of your building intuition. Which of these shading masks corresponds to these different shading devices? Here we have an infinite overhang. Is it A, B, or C? Somebody shout it out. I see some chats. Oh, that's just a question. C, yes, thank you. An infinite overhang looks like C because here on the horizon, the overhang starts and it covers some of that south-facing sky all the way from one horizon to the other horizon, projecting out a certain distance which corresponds to the profile angle, right? You're using a profile overlay here to determine what curve this shape would take. Overhang corresponds to A or to B. It corresponds to A because you've got that same shape of the infinite overhang, but on another profile angle, or rather on another profile curve from your loft sac, which corresponds to an angle taken from the center point up to this edge here. So there's your profile angle right there. You cut off that infinite overhang and you have just a normal overhang. And of course, this leaves as an infinite fin something that goes from at least as high up as the point of reference that you're interested in, because, at least as high up as the point of interest that you're interested in here, the horizon needs to be blocked. And then it goes up all the way into the sky, up to the zenith. And that's what an infinite fin would look like. Of course, if the top ends somewhere, then this top portion of the pie slice is not blocked. So you would not want to shade that. Window properties. Are you doing this, Jackie?
Yep, I got it.
Okay, thank you everybody for your attention and care to solar geometry.
Okay, so now I will quickly go over window properties. And there are all types of glass, and window performance is largely based off what you see on this NFRC rating label. NFRC is the National Fenestration Rating Council. So we're going to be looking at U factor, solar heat gain coefficient, visible transmittance, and not really that much at air leakage. And I will go over these 4 concepts in the next few slides. So first, there is U factor, and U factor corresponds to how well a window performs to conductance. So U factor equals the conductive heat loss through a window, and this includes both glazing and the frame. Glazing meaning the glass. You want to typically have a lower U factor. The lower, the better. And when you're looking at these numbers, they're typically around 0.25 to 0.4. Next, we have solar heat gain coefficient, also shortened as SHGC. The solar heat gain coefficient describes how much shortwave infrared a window emits. And this is only talking about the glazing. And you can figure this out by using emitted radiation over incident radiation. So this includes transmitted heat as well as the heat that is absorbed by window, then re-emitted. To have a better performing window, you want to have lower SHGC, because that means less solar heat is emitted. So to get a range of the numbers, these typically are 0.25 to 0.55. And then lastly, we'll talk about visible transmittance, and sometimes you see it as VT. So visible transmittance describes the proportion of visible light spectrum transmitted through a window. So basically this means how can we see an image through a pane of glass. And this is a value between 0 to 1. Even within these values, there are trade-offs between windows. Often a higher VT comes as a result of a higher SHGC. even though you want to have a lower SHGC, you do also really want to see outside of your window, because that means you have a higher VT means that more light is transmitted. More light is transmitted, meaning that you will have more daylight and also more view. So there are 5 cost-effective window technologies that we will describe. First, there's multiple panes. You always want to have at least 2 panes of glass. That has talked about triple and quadruple panes, but that's quite expensive. You have low emissivity coatings. So that was what we were talking about before, low E metallic coatings. Low conductance gas fills. So you'll see gases like argon put in the gap to create another barrier. Warm edge, low conductance spacers. And those are used to have a better frame for less thermal bridging. And then lastly, insulated frame systems. So actually having insulation within the metal frame, or that'd be difficult to do in wood. So yes, typically that's done in a metal frame. All of these methods reduce thermal bridging through a window system. Next, some brief concepts about daylighting. 2 terms that are highly confusing but important to distinguish in daylighting are illuminance and luminance. So illuminance is light incident on a surface. So light hitting a surface is what that is. This is the most common metric, but is not what the eye sees. It is the basis for most codes and standards, and the units are imperial, which is foot candles, and that equals lumens per square foot, or the metric units, which is lux, which is lumens per square meter. And to get a range of how you can figure that out, 1 foot candle is approximately 10 lux. And then on the other side is luminance. So luminance is light leaving a surface, and that is the brightness of that surface. This is the light that you see and the basis for glare. So when you see a glare analysis, they will always have the units of candelas per square foot or candelas per square meter. And Gail had this nice memory trick. I for illuminance can be tracked to incident. So illuminance is incident. And then L for luminance is light leaving, so LL. Okay, so a rule of thumb for daylighting is that 2.5 times H is the daylight penetration into a space. The height of the window is a critical dimension, and the height of the windowsill isn't as critical. You take the height, typically above the work plane, multiply it by 2.5, and that gets you a good sense of how far you can get good daylight penetration into a space. One thing to note is that when you're measuring the height of a window, some people take this measurement from the floor while others start at the work plane. This class, we typically take it from the work plane. But in either case, most important is that the height of the window is what makes the biggest difference in this rule of thumb. Next, we have daylight factor, and daylight factor is a static daylighting metric. It's the ratio of internal illuminance to external illuminance. Benefits is that they are widely used, widely defined, and very easy to measure and calculate. However, there are limitations, being that it's only for an overcast sky, and as we all know, we do not always get overcast skies. and is insensitive to orientation and time of day. So this is a way that the overcast sky simulator will be used for daylight factor. And you probably all remember these, as this is a big emphasis in the lecture and in the final design project. There are architectural strategies to reduce glare. This does not provide shading for the window, but provides a way to reduce the amount of contrast glare between inside and outside, because inside is typically very dark and it's very bright outside. So the strategies include light window frames, wall washing, windows on two sides of the room, thick or splayed window frames, clerestory windows, and light shelves. So I'm gonna explain light shelves a little bit further. The part of the element that extends outside can also serve as a sunshade for the lower view window, also blocking the view of bright sky, which is also a glare source. The part inside serves to reflect light further back into the space. The top surface should be reflective. As you're looking at that top image and the arrows, remember that a surface is if the surface was a mirror, or if it was like a mirror, the light will bounce like this, but that rarely happens. It's better to think that it will make one bounce, and you can't really assume too many bounces because, again, most surfaces aren't mirrors in a building. Okay, so that is it for daylighting. So I will now pass it on to Sierra for passive cooling.
Great, thank you. Okay, so I'm just going to go through a few different strategies for passive cooling that we talked about in the class. So focusing on four main ones: natural ventilation, thermal mass or earth sheltering, evaporative cooling, and then radiative cooling. So for natural ventilation, the purpose here is to remove heat from the body or the building structure. And so when you're designing for natural ventilation, you might use things like a raised floor, a narrow floor plate so that air can easily pass across the kind of length of the building. You might use high ceilings, also large windows. Second strategy would be using thermal mass or earth sheltering. So you could use the earth as thermal mass, kind of tucking a building into the ground like this to take advantage of that. The ability of the earth to be kind of a heat sink and be cooler in the summer than the surrounding air. You could also use a kind of earth tube and convective heat transfer to kind of run maybe the water for radiative floor and ceiling, a radiative system in the building, running that water through the earth to cool it down. So that's more of an indirect system. So there are kind of a few different options to incorporate thermal mass or earth sheltering, passive cooling. The third strategy would be using evaporative cooling. So taking advantage of that exchange of sensible heat with the temperature and latent heat in terms of humidity. So that could be a really good way to cool things down, similarly to how our bodies use sweat and evaporation of sweat off our skin to cool us down. So one way to do that would be using an evaporative cooling tower. So kind of running air through this tower and kind of a wet screen to kind of cool the air down before it moves into the interior of the building. Then the fourth strategy is using something like Skytherm for radiative cooling. So this is kind of like a roof pond system. So you might have these water-filled bags on the roof of the building acting as thermal mass. Then you can use the stacked insulation, which can either retract and leave the water exposed or expand back out and cover the the water to insulate it. So during the day, if you're using this for cooling, during the day you would keep the kind of thermal mass, the water-filled bags covered with the insulated panels. And then at night you could retract the insulation and let the heat stored in the water-filled bags radiate to the night sky. So that would be able to cool down the interior at night, and then if you're insulating during the next day, you'd hopefully be able to keep things cool and relying on that time lag from the thermal mass. Now I will pass it back to Jackie for everything else.
Okay, so we're just going to go over a little bit of everything else. First, there are the code and rating systems. One of the most rigorous energy efficiency standards in their building code. There is also a lot of other rating systems that we have studied. So to give a quick overview, LEED really looks at aspects of materials, daylighting, energy efficiency, and site considerations. The Living Building Challenge is like a very beefed up version of LEED with all criteria that must be met to be certified, and this includes water. WELL looks at human health and comfort and even considers nutrition of building occupants. Net zero energy buildings certified when buildings produce enough energy to offset the energy they use. So usually that is achieved through low EUI and renewable energy. And then there is Passive House, which looks thoroughly at the building envelope. Airtight and highly insulated envelopes are required for this rating. Title 24 is part of California's building code, and it is part 6 of the energy efficiency standards. Buildings must comply in California, and it's an effort to raise the minimum energy efficiency in California. So things that we have not covered, embodied carbon, materials and indoor air quality, decarbonization and electrification, HVAC, and sensory delight. So please review these concepts on your own. Sierra has seen a past exam that had a question about the refrigeration process, which is in the HVAC lecture. Since some of you did come in a little bit later, this is a reminder that a recording of this session will be posted onto the 1.4 YouTube channel if you want to refer back to Sarah's calculation review or Eric's stellar solar angle review. Also, these slides are posted on the B Courses Files page. Don't forget to go to the final exam. It's on Monday. Zoom link for the exam will be provided later, and all the exam updates are on the B Courses page. And we will now leave this session, or let the session just open up for questions.
Do you want to start a separate recording file of the questions section, or even not recorded? I'm not sure which is better.
Yeah, I think I'm going to stop recording now.
Yeah, that sounds better.
Yeah.